All right, that should be coming pretty soon. All right, so to recap, as soon as we're live, it's coming.
It says live in the corner.
Yeah, I think it just. All right, so the first group said we use CNC machine tools because they're accurate. Way to make it. Another idea is that it's an affordable way to make prototypes. I'll pull a couple more groups here. Let's see. There's the button. All right. Lily, you were in a group. What was your group's answer to this question?
Which question? Sorry.
Why are we using CNC machine tools to make prototypes?
We said along the same things as other people in terms of like accuracy, maybe more time efficient, prototyping something.
What was the last thing you just said?
And more time efficient if you're prototyping something.
Was there any group that had something else other than this that they think is really important to add now?
Less labor and less costly than making a whole new machine for it.
So low labor.
Also repeatability.
Did we mention fast turnaround time?
Nope, nobody said that yet.
Wouldn't that go under time efficient? Just wondering, what would the difference between those two be?
I would say that fast turnaround and time efficient are not necessarily the same thing. It really depends on the intent of the person who was saying it at the time, I suppose. But in my mind, fast turnaround means you say, I want this prototype, and I very quickly hand it to you. That's fast turnaround. And time efficient, it sort of tells me that although I may not finish the job very quickly, when I do the job, it doesn't take a lot of time. If you
Okay.
That's how I understood it when we talked about it. All right, so we like CNC machines because they're accurate. It may be more affordable than other methods of making stuff. So a lot of the stuff that we use, like, all right, so I got my headphone case here. This has been injection molded in the components, and then it was assembled, like the case itself. The electronics were made with other processes. So if we wanted to see if this design was going to work for our customer, it could take $50,000 maybe to make the molds to do this injection molding process. And so I like the idea of affordable, because even though the process of injection molding will make one of these cases, I don't know, every 25 seconds for almost no cost per case. Once you start the process, it's pennies per case. Once you start the process, to make the first one is going to cost about $50,000. So that's why I like the idea of it being affordable. Now the CNC machine tools do have a fairly. We haven't really talked about accuracy and precision. But so the definition of the word accurate means closeness to the correct value. And CNC machine tools can be very accurate. They can also be very precise, so they're very repeatable. And so that means that we'll know what we're going to get out of it. And so I like that. The fast turnaround and the time efficient. if you take into the idea, if we go back to the headphone case here, if you think about if we're going to injection mold these, we have to figure out how to design the molds. Then we have to manufacture the molds. Then we have to get it installed in a machine, in a production run. We have to figure out which plastic we're going to use and how to do that. And so I agree that we definitely can get a faster turnaround by billet machining this part than by trying to injection mold it. I would say that the injection molding process is more time efficient. And so once we go into production, we're not necessarily going to use the same manufacturing process to make the part. And that's one of the things that makes prototypes fairly unique, is that they don't always use the most time efficient process to make the part. You guys have seen beer cans, right? Or soda cans. I didn't mean you're looking at them now, but you've seen them.
Yeah.
Has anybody ever seen there's that How It's Made show?
Yes.
Right?
All the time.
Have you seen the How It's Made episode about how they make those cans?
Yep.
Anybody know what the largest can manufacturer in the world is?
Is
Yeah.
it Coke?
It's Coors.
Oh,
Just a bit of trivia there. At least they were when I had the data. I don't know. I don't actually track the size of can manufacturers on a daily basis. But all right, so the process that we make those is like a stamping process, right? And so you get sheet metal, and they've got with cans, they've gotten very good at making them because if you can increase the life of the die that does the stamping just a little bit, you can make the can manufacturer make a lot of money and things like that. So they've refined this process as much as they can. So I worked on a project with a WPI alum, and he wanted to make something that was sort of shaped like a can, and he wanted to make it out of aluminum. So you could basically use the can process to make these things, except it was a different shape. And so you'd have to make special tooling to make it with that process. So when we get to production, you totally would use the same process they use to make soda cans or beer cans. But he needed to have about 50 of them so that he could put his product in it, and then he could see if anybody wanted to buy his product. And so we did a prototype production run where we billet machined the parts out of blocks of aluminum. Almost probably 99.99% material removal. The thickness of the thing that was left over was 3/1000 of an inch on the bottom, and it was 20/1000 of an inch all the way up the sides. Clearly not the most efficient process to make those parts, but it was cheaper than building a factory to make those parts just to see if anybody wanted to buy it. So that's what makes a prototype unique. Now, if you're doing a first article, you guys heard of first article before? Some group that had talked about this. What did you guys come up with for what's the difference between a prototype and a first article?
The first article is like the first actual product made on the final machines.
Exactly. So with a prototype, we can make it the part using any process as long as it makes the physical part that our customer, if we're the prototype manufacturer, as long as it makes the physical part that our customer wants to see. A first article has got to be made on the production machine. Whatever machine we're going to use to do that production, we've got to use that process exactly when we make this first article. Now, the value of the first article is it allows us, and often the first article it takes many, many pieces before you give the first article to the customer. right? Because you have to refine the process. You have to figure it out, especially if you're trying to improve the time efficiency. If you make a change in your process as you're making these parts, you've got to then internally at least do another first article type inspection where you're basically checking all the dimensions that are on the drawing. You're checking to make sure everything is within the tolerance when you make that first article, similar to when you're doing a prototype. When you make a prototype, you've got to check all of the important dimensions to make sure that you've made it correctly. When you're doing production, at volume production, you may own, I mean, we've talked about that. You only sample every 100th part maybe, or every 1,000th part. But not only that, you don't necessarily check all of the dimensions. You don't necessarily check all of the specifications as long as you know your process is in control. So there's a lot of similarities between a first article and a prototype, but I wanted to point out the difference is the prototype, you can use any machine to make it. And that first article, you've got to make it on the machine that's going to be making the parts in production, the parts that you're going to be sending to the customers. All right. Whether it's a prototype or a product that you're sending out for first article manufacturing, who's responsible for the design?
The engineer, or like the person who.
I like to call this person the designer.
The designer.
Yeah.
Right. And I think intuitively we get that, but the manufacturer, and there's instances, especially small companies that have products, the designer and the manufacturer are the same person. The designer and the manufacturing engineer are the same person. When you're doing your MQP, and I'm guessing many of you intend to do an MQP before you leave WPI. And if not, you might as well just leave now. When you're doing your MQP, if you're going to be making stuff for your MQP, you're going to be the prototype manufacturer and you're going to be the designer, probably. Now, it could be you divide your group up. Somebody in the group does design work and somebody in the group does manufacturing work. Those two people should be talking to each other because the group is both the designer and the manufacturer. So the designer is responsible for the design part of the prototype. I think if I escape, come here and click escape. That didn't do what I expected it to do at all. Now I drag it back over here. And I click this blank slide. Okay. What are the things that the designer has to design?
A CAD file or something that can
So
go.
the designer may use a CAD file to get the information to the manufacturer. But what are the things that the designer has to choose? These are the design parameters, right? That was the next question. What are design parameters? Design parameters are the things the designer has to choose. I want some examples of design parameters.
The materials.
All right, so the designer chooses materials.
The cost.
The designer does not choose cost. They may choose how much they're willing to pay. They may choose value, but they don't choose cost.
The dimensions.
Dimensions.
Color.
Color. What else?
Like target physical properties, like
So physical properties.
Function.
Oh, like the texture.
Like physical properties like strength, ductility, strength, ductility, hardness.
Would they choose the texture?
Now, a lot of the things that define these physical properties that we just said come from the material specification. So I'm gonna see if I can drag this down here. But it's not just the material, the physical, what material is it? Because it's also, are there heat treating things that have happened to that material? So somebody said something else when I was talking.
The
Surface
function.
finish.
Say again?
Like surface finish, like if it's rough edged or smooth.
So what else does the designer choose?
The assembly process.
No. The designer does not choose the assembly process. However, I think what you were getting at was tolerances, right?
Yeah.
If two parts have to interact with each other, the designer has to understand, like when we had our cylinder and piston. Oh, I've lost all my pistons. I just have cylinders now. But the designer has to know what's the allowance that we will give between these two parts if they're going to work together. So tolerances. And there's a tolerance on each of the other design parameters. They may not call it out independently, but every design parameter has a tolerance. What else? Anything else the designer chooses?
Potential use of customers.
So yeah. So before you even get to the designer, you have to have the idea phase, right? There's an ideation phase in this process of understanding a customer need. And then your design is the process that you think you can meet that customer need, right? So the designer has to understand what the customer needs. And so we're talking about design of a physical product. Actually, no. It pertains to software product design also, right? You've got to understand what the customer needs if you're going to design software for them too. Anything that you're going to design, you've got to understand the customer needs. And then you come up with functions that would meet the customer's needs. And then you come up with design parameters so that you can tell the manufacturer how to make something that meets those functions. Is there anything that we missed here that's big? We got physical dimensions, surface finish, color, bulk material properties, and tolerances.
You add like risk, like if you're designing like a high risk part versus a low risk.
You're going to consider that when you pick the physical properties and the tolerances, I think. So
Okay.
You've got to consider it, but the design parameters are the bits of information that you have to give the manufacturer in order to get the part back that you need. And so you may want to communicate things like your vision of the risk of failure of the part when you talk to the manufacturer. But when you do that, it's because you realize that you may have made a mistake and the manufacturer may have a better idea to help you with your design. And so very arrogant designers will never tell the manufacturer anything. In fact, at our small company, we often get drawings for parts that they can't tell us what the part is used for. And they tell us, here's the material, here's the shape, here's the tolerances, give us a price, we'll let you know if we want to buy any of the parts. And they won't even tell us what the parts are used for. Those are usually because there's some Defense Department use down the road somewhere, and I don't have the right security clearance to know that. It's often easy to figure out when you go visit the guy's office and there's pictures of airplanes all over the walls, and it's all pictures of the same airplane. You can usually figure it out, but they can't tell you. Okay, so the designer picks these things. What are process variables then?
How the physical process of machining the part changes. Like if you're going to need to use a mill versus a lathe.
All right, that was Sam, right?
Yeah.
So I agree. The type of machine tool you've decided to use and the type of machining process, whether it's turning or milling, that you've decided to use, those are examples of process variables. In a quick statement though, what are process variables? So those are two or a good example of a process variable, but what is process variable?
Is it what the manufacturer gets to pick?
It's what the manufacturing engineers get to pick. Now, I'm using the word manufacturing engineer in a very broad sense here. It could be the guy on the shop floor putting the part in the machine tool that's picking some of these process variables. If you as the manufacturing engineer, for example, haven't told them how tightly to tighten the handle on the vise, and the vise is clamping the part and withstanding the cutting forces from the machining operation, if you haven't told them how tight to tighten the vise, then they're going to use their judgment every time they close the vise handle. And they then are picking that process variable, not you. So, but it's the things we get to choose. So what are some examples? So machine tool. And so machine tool type, that's an example that we've talked about. What else do we get to pick?
Would another thing to pick be the difference between like milling and turning?
So yeah, so machine tool type, machining process type.
Could also be like the feed and speed.
Speed.
How you zero out your axes?
The origin. So the spot on the workpiece material or the spot inside the machine tool where we've decided we're going to reference all of our dimensions from. So work zero. We call that work zero. Oh, hey, by the way, did you guys all get the email from the president? They said we're allowed to come back to class again. Don't screw it up over the weekend because we're going to start on Monday with in-person labs for people that are not fully remote. Between now and then, I got to find out who's who. I will put a like a survey in the announcement in the Canvas site when we're done with class that asks you to tell me if you're going to stay remote or if you're going to be on campus. And the way we're going to do the in-person lab exercises is you've all got a 2-hour block that we've been using for Zoom help hours right now for learning CAM for last week and this week. During your scheduled 2-hour block, there will be a 35-minute window where we will expect you to be standing in front of a machine tool in the lab. You need to arrive on time so that you get your 35 minutes in, and then you got to leave on time so the next person can start. And that way we can keep it so that we have big enough spacing in the facility so that you guys aren't next to each other and we don't spread disease and all that stuff, right? We're worried about spread of disease these days, right? We should always be worried about spread of disease, but I guess we're taking it more seriously this year. And so you'll all get about an hour in front of a machine tool or doing some other exercise in the lab each week while you do that. We're going to continue to use the Wednesdays as lab lectures. And if as you're doing the CAM exercises, so learning how to do the programming, if you have questions about the current exercise, or if you have CAM questions at all, be prepared to talk to them either before or after. Be prepared to talk to the PLAs in the lab either before or after your scheduled 35-minute window. And that way you can, and we've got computers in the lab that run all the CAM software, so you guys can, you can log in if you got something you're having trouble with. You can log in, the PLA can help you get through that. And we're going to be doing some evening hours of Zoom help and some other hours during Wednesdays and Fridays for help on doing the CAM exercises, stuff like that. That will start on Monday next week. So if you're in section 1, you'll have lab on Monday and Wednesday. If you're in section 2, 3, or 4, you'll have lab on Tuesday and Thursday. But I'll put that survey out so I can get you guys all assigned to your 35-minute time windows. Next week, we are going to make the Y blocks for our Stirling engines, and we're going to make the cylinders for our Stirling engines.
So does that mean we still get our kits from the bookstore?
We get the kits from the bookstore, and the kits should be at the bookstore this afternoon. They're almost all fully assembled now. We had some manufacturing issues on the kits. The loose nut behind the keyboard.
Do you know if we need to order it online, or can we just go walk in?
Just go pick it up. You don't have to order it online unless you want them to ship it to you.
Okay.
Okay, process variables. All right, so I get distracted by the joy of going back to school. I guess, so there was a blip in new COVID cases last week on campus, but I guess they figure after they've tested everybody a couple times, they know who's got it and who doesn't, and that it's safe for us to come back. So that's exciting. We had our staff meeting yesterday morning, and we looked at the dashboard and we said, yeah, they're going to push it out at least another week. And boy, were we wrong, because right after that, the email came out from the president. So, all right. Manufacturing engineers get to pick it, machine tool type, the process type, feed speed.
You said the amount of waste, like the amount of scrap generated, or the amount of like energy being used?
So, yes. But usually we don't pick the amount of energy being used directly, but it certainly can be a factor in why we pick some of the other parameters. I like that. This is, and you meant energy being used as in, so we don't waste energy, so we don't kill the environment, correct?
Yeah, like using the machine efficiently. So
yeah, that's what I took your meaning to be. So next week, we're going to actually talk about how we can understand how much energy is going to be used based on knowing stuff about the manufacturing process without even being near the machine tool. We're also going to talk about how we can measure how much energy was used, whether we're near the machine tool or not. All right. So we pick other things in order to control that. So we have feed speed. I want to put right next to that depth of cut. And so the depth of cut is on our turning operation as we're spinning the workpiece around. It's how far in and out towards the workpiece we are when we move across. Or in a milling operation, it's how far down we are relative to the top of the workpiece and how far stepped into it we are. So depth of cut has 2 dimensions in milling. It's axial depth and radial depth. And we're going to talk more about this on Thursday this week. The whole lecture is just about feed speed and depth of cut on Thursday. Feed speed and depth of cut are the 3 most important process variables that we will choose for CNC manufacturing or CNC machining. All right. More important than those would be whether or not we're going to do CNC machining. Deciding if we're going to do milling or turning. No, feed speed, depth of cut, more important than deciding whether you're going to do milling or turning. Deciding whether you're going to do milling or turning just figures out what feed speed, depth of cut mean. So we're going to spend Thursday just talking about feed speed, depth of cut. The work zero is where on the workpiece we've decided our origin is. You guys did that in chapter 1, I think, in Getting Started with Cam. What else are process variables that we get to choose? Oh, yeah. This last one that I wanted to write down. You said energy, but you also said waste material, how much waste there is. The stock material. Now, not the material properties of the stock. The designer defines that. But the geometry of the stock material, we get to choose which piece of material we're going to cut this out of. So stock material. What else do we got? What else are things that we choose as manufacturing engineers?
Going off of stock material, could you say like capacity, like how many parts you can design from a certain amount of material?
So that goes along with choosing the stock material, the bulk material, yeah, or the stock. I'm going to delete the word material and just say stock, because the material part of it the designer chooses, but the stock and the geometry and the physical condition of it before we start, yeah. What else?
When to use coolant?
Coolant on or off. What else?
There's fixturing.
Fixturing. So fixturing is how we hold on to the part inside the machine tool. We're going to have a whole lecture on fixturing by itself. Plus, we'll talk about it in lab.
Oh, the plates, the two parallels that you put in the vise.
That's part of fixturing, sure.
Oh, okay.
What about production rate? Like how fast can you manufacture it?
I'm going to call that material removal rate, since we're talking about and material removal rate 100% depends on feed speed and depth of cut. But it's sometimes the reason that we choose the feed speed and depth of cut that we chose, is that material removal rate. There's different efficiencies depending on how fast you go. When we get to the economics part of the class, like week 5 or so, we're going to focus a whole bunch on this. But material removal rate also determines how much energy it's going to take to make the part. And how much energy it's going to take to make the part determines what the cutting forces are going to be. The cutting forces determine how much fixturing force we need to have in order to keep the part in the machine tool, and whether or not the tool that we're using is going to break. So material removal rate is very important, although it's factored from feed speed and depth of cut. What else do we choose? What time of day it is? Temperature. Temperature in the machine. I don't smell real good. You get it, right? Temperature in the machine tool, the temperature of measurement. We get to decide how to measure. What's our measurement plan?
Wait, sorry, Professor.
Yes.
What does temperature of measurement mean? Is that like when you measure it at a given temperature to see the expansion and contraction?
So if I have this brass part here, and I want to accurately control the diameter of the brass part, every time I measure the brass parts, they have to be the same temperature as each other because of that K, because of that material expansion coefficient. If I have a part that's made out of silicon carbide, it doesn't matter what the temperature is when I measure it because the K factor for silicon carbide is almost 0, 1. It almost doesn't expand at all with temperature. Whereas something like brass expands a lot with temperature.
Why does the time of day we cut matter?
Time of day. Could be day of the week too. Is there sun shining in through the window on my machine tool warming it up? Is the person who's going to be operating the machine tool fully awake and alert? Is there a train going by when I make my measurement? Or when I run the finish pass on the part? Now, things like time of day and temperature matter when we have very tight tolerances and when we have hard to control processes, typically. So if we have a very robust process, and it's not going to matter. But those are all things that we get to choose. They're all things that could influence the part quality. And remember, quality is giving the customer what they need when they need it. And if we cannot give the customer what they need when they need it, our company will fail, and then we'll have to go back and live at mom and dad's house.
Just to be clear, can all these PVs be controlled in CAM software?
With exception of things like time of day and temperature, yeah. Those are that's the sort of the purpose of the CAM software is to help you choose these things and to automate the process of choosing these things. Tomorrow we're going to be back here on Zoom. Tomorrow I'm going to talk about the group project. I'll give you a little heads up though. The group project is going to be, imagine you're creating a startup company and you've got a part that you're going to manufacture and sell. Your group project is going to be to figure out how much it's going to cost you to start the company, and then how much you have to sell the parts for in order to make back the money that you had to invest to start the company. And so we'll spend, well, the rest of the term, it'll be due the last week, and we'll be talking about the things that you need to consider throughout the rest of the term. I'll stick around for questions if anybody has them, but I think we're out of time.
Thank you.
Thank you.
Thank you, Professor.
Thank you.
Thank you.
Thank you.
I have a question.
Yeah, Professor.
We just, I'll go ahead and stop the live video here. I don't know if I can find it. Stop. All right, I guess I have to stop the share. And